vLLM versus TensorRT-LLM versus Ollama versus llama.cpp, choosing the right inference engine on RTX 5090. Why this comparison exists. I've been running Nematron Nano 9BV2 Japanese on an RTX 5090 with vLLM 0.15.1 for months now. Before settling on vLLM, I evaluated TensorRT-LLM, considered Ollama, and benchmarked llama.cpp. This article captures what I learned, not from reading docs, but from actually trying to get each engine running on consumer Blackwell hardware. The short version, vLLM 1. But the reasons are more nuanced than it's the best. Each engine occupies a different niche, and the right choice depends entirely on your hardware, model architecture, and use case. The 4 contenders at a glance. Feature vLLM TensorRT-LLM Ollama llama.cpp. Primary focus production serving maximum throughput simplicity portability. Quantization AWQ, GPTQ, BF16, FP8 FP8, FP4, INT8 GGUF, via llama.cpp, GGUF, Q4_K_M, Q5_K_M, etc. API OpenAI compatible custom plus Triton OpenAI compatible, server mode. Setup difficulty medium, source build for 5090, hard, Docker/ngc required, trivial, easy. RTX 5090 support yes, v0.15.1 plus, partial, SM120 kernel gaps, yes. Continuous batching yes, paged attention, yes, in-flight batching, no. Mamba/SSM support yes, limited via GGUF only vLLM, the pragmatic choice. What it does well. vLLM's core innovation is paged attention, treating KV cache like virtual memory pages. This eliminates the memory waste that plagues naive implementations and enables efficient continuous batching. On my RTX 5090 running Nematron 9B and BF16. Single request, 83 TOC/S. TTFT, 45 to 60 milliseconds. Batched, 10 concurrent 630 TOC/S. VRAM usage, 30.6/32 GB. That batched throughput, 7.5x single request speed, is the real story. If you're serving multiple users or running batch processing pipelines, this matters enormously. The OpenAI compatible API. vLLM exposes a drop-in replacement for the OpenAI API. Every tool in the Python ecosystem that speaks OpenAI's protocol, LangChain, Llama Index, custom clients, just works. Then from any client. The pain point, installation on RTX 5090. Let's be honest, installing vLLM on Blackwell consumer GPUs was painful in early 2025. A simple failed because PyTorch didn't support SM120, Blackwell's compute capability. You needed nightly PyTorch builds, CUDA 12.8+, and sometimes source compilation. As of March 2026 with vLLM 0.17+, the situation has improved significantly. The CUDA 13 nightly will stack works out of the box. But if you're on an older setup, expect to spend an afternoon wrestling with dependencies. Why it won for my setup? Nematron uses a Mamba-hybrid architecture, SSM plus transformer layers. vLLM has native Mamba support via. This was the decisive factor, none of the alternatives handled this architecture as cleanly. TensorRT-LLM, faster, but at what cost? Raw performance. TensorRT-LLM is genuinely faster in raw throughput, 20 to 100% depending on quantization, and FP8 support is its biggest advantage. On H100 clusters with pure transformer models, it's the undisputed king. Batch 128 throughput on 8 times H100, for 800 TOC/S, versus vLLM's 3 for 100 TOC/S. TTFT at batch 1, less than 10 milliseconds. FP4 quantization on Blackwell data center GPUs, exceptional. Why I skipped it. For my RTX 5090 setup, TRT-LLM didn't make sense for 4 specific reasons. 1. Mamba-hybrid architecture support is still rough. TRT-LLM's Mamba 2 support is limited, and Nematron's hybrid architecture hit edge cases that produced incorrect outputs. 2. RTX 5090 FP8 kernel support wasn't there when I evaluated. Consumer Blackwell, SM120, kernels lagged behind data center Blackwell. Error messages like fallback to unfused MHA for data_type equals BF16 in SM_120 were common. 3. Installation is Docker or bust. The recommended path is an NGC container. Building from source requires NVIDIA's internal build system knowledge. For a solo developer on WSL2, this adds friction that vLLM doesn't have. 4. The speed gain at BF16, no quantization, shrinks to 10–30%. Without FP8, vLLM's 630 TOC/S batched throughput was already sufficient for my workload. When TRT-LLM makes sense. You're running pure transformer models, not Mamba-hybrid. You have H100/H200/B200 data center GPUs. You need FP8 or FP4 quantization for maximum throughput. You have a team that can handle the DevOps complexity. You're optimizing for cost per token at scale. If you're a solo developer on consumer Blackwell hardware running Mamba-hybrid models, TRT-LLM is not the pragmatic choice, at least not yet. Ollama, great for demos, wrong for production. What it does well. Ollama is the vLLM inference. One command to install, one command to run. It wraps llama.cpp internally, provides a clean CLI, and maintains a model library that makes downloading models trivial. For trying out a new model in 30 seconds, nothing beats it. Why it's not enough for serious work. 1. No continuous batching. Ollama serves one request at a time. If you're building a pipeline that sends multiple concurrent requests, throughput collapses. My vLLM setup handles 10 concurrent requests at 630 TOC/S total. Ollama would serve them sequentially at 83 TOC/S each. 2. GGUF only. Ollama uses llama.cpp's GGUF format exclusively. This means no native BF16/FP16 inference, no AWQ/GPTQ, and no page detention. You're limited to the quantization levels GGUF supports. 3. No Mamba/SSM support beyond what's available in GGUF format. Nematron's hybrid architecture doesn't work well through the GGUF conversion pipeline. 4. Limited GPU utilization. Without continuous batching, your $2,000 GPU sits mostly idle between tokens. On an RTX 5090 with 1.79 TB per second memory bandwidth, this is a waste. 5. No speculative decoding, no tensor parallelism, no prefix caching. The advanced serving features that make vLLM and TRT-LLM production ready are simply absent. When Ollama makes sense. Quick model evaluation and experimentation. Personal chatbot for interactive use, one user, one conversation. Machines without CUDA, Ollama supports CPU and Apple Silicon. You don't want to think about Python environments or CUDA versions. Llama.cpp, the Swiss Army knife. What it does well. Llama.cpp is the foundation that Ollama builds on, but with full control exposed. Its GGUF quantization format is remarkably efficient. A Q4_K_M quantized 7dB model fits in 40 GB, runnable across two RTX 5090s. Key strengths. CPU/GPU hybrid inference, split layers between GPU VRAM and system RAM. Broad hardware support, CUDA, Vulkan, Metal, CPU, runs everywhere. Excellent quantization, Q4_K_M, Q5_K_M, Q6_K offer good quality/size trade-offs. Active development, the most actively maintained inference project on GitHub. RTX 5090 performance, llama.cpp. Community benchmarks show strong single GPU numbers. 8B models, 185/213 TOC/S, token generation. 32B models, 61 TOC/S. Prompt processing, 8B10 for 100+ TOC/S prefill. 147K context on 30B Mo, stable at 52 TOC/s. These are competitive numbers for single request inference. The 1.79 TB per second GDDR7 bandwidth of the RTX 5090 is a huge advantage for the memory-bound token generation phase. Why it wasn't right for my setup. 1. No continuous batching in the server. Like Ollama, llama.cpp server mode handles requests sequentially. For a multi-service architecture where multiple apps query the same model, this is a bottleneck. 2. GGUF conversion quality for Mamba-hybrid models is uncertain. Converting Nematron's mixed SSM/transformer architecture to GGUF risks losing accuracy in ways that are hard to verify without extensive benchmarking. 3. No native OpenAI-compatible reasoning parser. vLLM's plugin system let me write a custom reasoning parser for Nematron's thinking tokens. Llama.cpp server has more limited extensibility. 4. Lower batched throughput. While single request speed is excellent, the lack of page detention means multi-user serving is fundamentally less efficient. When llama.cpp makes sense. CPU-only or hybrid CPU/GPU inference, models too large for VRAM. Cross-platform deployment, macOS, Windows, Linux, even Android. Edge/embedded scenarios where vLLM's Python stack is too heavy. Quantization experimentation, GGUF offers the widest range of quant levels. Single-user interactive chat where batching doesn't matter. The decision matrix. Your situation best choice why. Production API serving, multiple concurrent users vLLM page detention, continuous batching, OpenAI API. Maximum TOC/s on H100/B200, pure transformer TensorRT-LLM 35 to 50% faster raw throughput, FP8/FP4. Quick model testing, personal chatbot Ollama 0 setup, model library, just works. CPU/GPU hybrid, cross-platform, edge deployment llama.cpp runs anywhere, efficient quantization. Mamba-hybrid models on consumer Blackwell vLLM native SSM support, manageable setup. Solo dev, RTX 5090, need OpenAI API vLLM best balance of performance and usability. My stack, how it all fits together. All services hit the same vLLM instance via OpenAI compatible API. Continuous batching handles concurrent requests from multiple apps without dedicated GPU allocation per service. 1 GPU, 1 inference engine, 13 plus projects. Conclusion. The LLM inference engine landscape has consolidated around a clear hierarchy. vLLM for flexible production serving, 85% of open model inference in production uses vLLM, TRT-LLM, or TGI. TensorRT-LLM for maximum NVIDIA-optimized throughput. Llama.cpp for portability and edge deployment. Ollama for frictionless experimentation. For a solo developer on consumer Blackwell hardware running Mamba-hybrid models, vLLM is the pragmatic choice. TRT-LLM's raw speed advantage doesn't justify its complexity when your bottleneck is architecture support, not tokens per second. And Ollama/llama.cpp, while excellent tools, lack the serving features that make a single GPU serve an entire project portfolio. The gap between these engines continues to narrow. TRT-LLM's lead has shrunk from 2-3x to 35 to 50%, and vLLM's installation story on Blackwell is finally improving. By the time you read this, some of these pain points may already be resolved. But the architectural differences, continuous batching, page detention, native SSM support, are fundamental design choices that won't converge anytime soon. Choose the engine that matches your actual constraints, not the one with the highest benchmark number.